Dmitri Ivanovich Mendeleev was born on February 8, 1834, in Tobolsk, a remote Siberian town near the edge of the Russian Empire. He was the youngest of at least 14 children, accounts vary between 14 and 17, born to Ivan Pavlovich Mendeleev, a local schoolteacher and director of the gymnasium, and Maria Dmitrievna Kornelieva, who came from a family of Siberian merchants and old believers. Tobolsk was a place of exile, where political prisoners and criminals were sent to serve their sentences in the harsh Siberian wilderness. It was a frontier town, isolated from the cultural centers of Moscow and St. Petersburg, yet it had its own small intellectual community. Young Dmitri grew up in this world of extremes, bitter cold, long distances, and a family that valued education despite their modest circumstances. Tragedy struck early. When Dmitri was 13, his father went blind and lost his position. The family's finances collapsed. His mother, Maria, was a remarkable woman, strong-willed, intelligent, and determined that her youngest son would receive a proper education despite their poverty. She took over managing a glass factory that her brother owned, working tirelessly to support the family. But disaster followed disaster. The factory burned down. Then, in 1847, Dmitri's father died. Maria was left nearly destitute with several children still dependent on her, yet she refused to give up on Dmitri's education. She understood he was exceptional, that he had a mind that needed cultivation. In 1849, Maria made an extraordinary decision. She would take 15-year-old Dmitri and his sister, who was also still at home, and travel thousands of miles to Moscow to secure him a place at the university. It was an audacious plan for a nearly penniless widow from Siberia. They traveled by horse-drawn cart and on foot, a journey that took months across the vast Russian landscape. When they finally reached Moscow, Dmitri applied to the university and was rejected. As a Siberian, he couldn't attend Moscow University. They only accepted students from the local region. Maria refused to give up. They traveled another 400 miles to St. Petersburg, arriving exhausted and nearly out of money. In St. Petersburg, Maria used every connection she had. Her late husband had studied at the main pedagogical institute, and she pleaded with the director to accept her son. Dmitri was examined, and despite his provincial education, showed such promise that he was admitted. It was the opportunity that would change his life, and eventually the history of chemistry. But Maria Dmitrievna would not live to see her son's triumph. She died shortly after securing his admission, worn out by hardship and the exhausting journey. Dmitri never forgot her sacrifice. Years later, when he published his masterwork on chemistry, he dedicated it to her memory. This investigation is dedicated to the memory of a mother by her youngest offspring. Conducting a factory, she could educate him only by her own work. She instructed by example, corrected with love, and in order to devote him to science, she left Siberia with him, spending thus her last resources and strength. Life at the main pedagogical institute was difficult. Mendeleev was poor, often ill with tuberculosis, a disease he would battle for years, and behind his classmates in many subjects due to his provincial education. But he had an extraordinary capacity for work and a mind that grasped the fundamental patterns underlying natural phenomena. He studied chemistry, physics, and mathematics, absorbing everything with fierce intensity. His professors recognized his potential. One, in particular, would change his life: Alexander Voskresensky, a chemist who introduced Mendeleev to rigorous experimental method and the latest developments in European chemistry. Mendeleev graduated in 1855 at age 21, but his health was poor. The tuberculosis was getting worse, and doctors gave him only 2 years to live. He was sent to the milder climate of Simferopol in Crimea to recover, where he took a position teaching science at a gymnasium. The Crimean War was just ending, and the region was recovering from the conflict. Mendeleev threw himself into teaching despite his illness, and gradually his health improved. Within a year, he had recovered enough to return to St. Petersburg, where he took a position at the university and began serious research in chemistry. In 1859, the Russian government awarded Mendeleev a fellowship to study abroad. He went to Germany, spending time at Heidelberg working with Robert Bunsen and Gustav Kirchhoff, two of the greatest experimental chemists of the era. Heidelberg was a revelation: access to the latest equipment, discussions with leading scientists, exposure to cutting-edge research. Mendeleev set up his own laboratory in his apartment and began working on the properties of liquids and gases, particularly studying critical temperatures and molecular forces. These investigations, while important, weren't revolutionary. Mendeleev was still finding his direction, still searching for the problem that would define his career. He returned to Russia in 1861, just as the country was undergoing massive changes. Tsar Alexander II had emancipated the serfs, and Russia was attempting to modernize. There was a hunger for scientific knowledge, a sense that Russia needed to catch up with Western Europe in technology and industry. Mendeleev became a professor at the Technological Institute in St. Petersburg, then at the university. He was a dynamic lecturer, though also demanding and sometimes temperamental. Students remembered him as passionate about chemistry, capable of making the subject come alive, but also capable of explosive anger if they didn't meet his standards. In 1862, Mendeleev married Fizva Nikitichna Leshcheva, the daughter of a family friend. The marriage was not happy. They were poorly matched in temperament, and Mendeleev's obsessive focus on his work left little time for domestic life. They would have 2 children together, but the relationship was strained from the beginning. Mendeleev's personal life would remain complicated throughout his career, with his professional obsessions often taking precedence over family obligations. But in 1867, Mendeleev received an appointment as professor of chemistry at St. Petersburg University, finally achieving the security and resources he needed for serious research. He was 33 years old, and the stage was set for his breakthrough. In 1867, Mendeleev faced a practical problem. He was teaching general chemistry at St. Petersburg University, but there was no good Russian textbook. So he decided to write one himself, Principles of Chemistry, which would become a landmark text. But as he worked on organizing the material, particularly the section on elements, he confronted a puzzle that had bothered chemists for decades. Was there any underlying order to the elements? By the 1860, about 60 elements were known, each with its own properties: atomic weight, valence, reactivity, and so on. Some chemists had noticed patterns. Dobryner had found triads of similar elements. Newlands had proposed a law of octaves, but these attempts at classification were incomplete, often contradictory, and generally dismissed by the scientific community. Mendeleev became obsessed with finding the pattern. He wrote the name of each element on a card, along with its atomic weight and key properties. He arranged and rearranged these cards, looking for regularities. He tried organizing them by atomic weight, by valence, by chemical properties. Days turned into weeks as he worked on the problem, barely sleeping, consumed by the puzzle. According to legend, and Mendeleev himself later told this story, the solution came to him in a dream on February 17, 1869. He had been working on the problem for 3 days straight without rest. Exhausted, he finally fell asleep, and in his dream, he saw the elements arranging themselves into a table where everything fell into place. When he woke, he immediately wrote down what he had seen. Whether or not the dream story is literally true, and Mendeleev may have embellished it, what is certain is that in February 1869, Mendeleev published his periodic table. But his table was different from previous attempts at classification. First, he arranged elements by atomic weight in a table format, with elements of similar properties falling into vertical columns. Second, and this was revolutionary, where the pattern demanded an element but none was known, Mendeleev left a gap. He predicted that these gaps represented undiscovered elements. Third, in a few cases where strict ordering by atomic weight would place an element in the wrong column based on its chemical properties, Mendeleev reversed the order. He trusted the chemical pattern over the atomic weights, suggesting that some atomic weights might be measured incorrectly. Most audaciously, Mendeleev made detailed predictions about the properties of the missing elements. For 3 gaps in his table, he predicted not just that elements should exist, but specified their atomic weights, densities, melting points, and chemical behaviors. He called these elements ekaboron, eka-aluminum, and ekasilicon, eka meaning one beyond in Sanskrit, indicating they came one position after boron, aluminum, and silicon in the table. These weren't vague guesses, they were specific, testable predictions. If Mendeleev was right, these elements would be discovered with exactly the properties he specified. If he was wrong, his table was just another failed attempt at classification, and he would be dismissed as other chemists had been dismissed before him. The scientific community's initial reaction to Mendeleev's periodic table was mixed. Some chemists found it interesting but speculative. Others thought it was overly complex or based on unreliable atomic weight data. Many simply ignored it. Periodic systems had been proposed before and had gone nowhere. Mendeleev had published in a Russian journal, and it took time for his work to circulate in Western Europe. But Mendeleev promoted his table vigorously, publishing in German journals, giving lectures, corresponding with chemists across Europe. He was convinced he had discovered something fundamental, a natural law as important as Newton's laws of motion. Then, in 1875, 6 years after Mendeleev's prediction, French chemist Paul-Émile de Buisbaudon discovered a new element in a sample of zinc ore. He named it gallium after Gaul, the ancient name for France. When he published the properties of gallium, Mendeleev immediately recognized it as his eka-aluminum. The atomic weight, density, and chemical properties matched his predictions almost exactly. When there were small discrepancies, Mendeleev wrote to de Buisbaudon suggesting he had made measurement errors. De Buisbaudon was initially indignant. Who was this Russian telling him he'd measured his own element incorrectly? But when he repeated the measurements more carefully, he found that Mendeleev had been right. Gallium's properties were exactly as Mendeleev had predicted. The discovery of gallium was a sensation. Here was proof that Mendeleev's table wasn't just an organizational scheme but a predictive tool, revealing a deep pattern in nature. But there was more to come. In 1879, Swedish chemist Lars Fredrik Nilsson discovered scandium, Mendeleev's ekaboron. Again, the properties matched the predictions. Then, in 1886, German chemist Clemens Winkler discovered germanium, Mendeleev's ekasilicon. Once more, Mendeleev's predictions were vindicated. 3 predictions, 3 discoveries, all confirming that the periodic table captured something real about the structure of matter. The chemistry community was convinced. Mendeleev wasn't just organizing known elements, he was revealing a fundamental law of nature. But Mendeleev's triumph was about more than predictions. His periodic table implied that the elements weren't just random building blocks, but were related to each other in a systematic way. It suggested that atomic weight was a fundamental organizing principle, though not the only one, since Mendeleev had been willing to reverse the order in a few cases. Most profoundly, it suggested that there was some underlying structure to atoms, some reason why elements with certain atomic weights had similar properties. Mendeleev himself didn't know what that reason was. Atoms were still mysterious in the 1870s and 1880s, but he insisted that his table revealed a deep truth about matter. He was right, though the full explanation would have to wait for the quantum mechanics of the 20th century. Honors began to accumulate. Mendeleev received the Davy Medal from the Royal Society of London in 1882, the Copley Medal in 1905, and honorary doctorates from universities across Europe. He became internationally famous, Russia's most celebrated scientist. But there was one honor that eluded him, the Nobel Prize. When the Nobel Prizes were first awarded in 1901, Mendeleev was nominated for the Chemistry Prize, and many expected him to win. But the Swedish Academy, for reasons that remain debated, chose not to award it to him. Some said it was because his discovery was too old, from 1869, over 30 years earlier. Others suggested professional jealousies or disagreements about priority, since other chemists had proposed periodic systems around the same time. Whatever the reason, Mendeleev never received the Nobel Prize. He died in 1907, just 1 year after it might reasonably have been awarded to him. While Mendeleev's scientific reputation soared, his personal life remained complicated. His first marriage had been unhappy from the start, and by the 1870s, it was effectively over, though divorce was difficult in Orthodox Russia. Then, in 1876, Mendeleev met Anna Ivanovna Popova, a young art student. He was 42, she was 16. He fell passionately in love, a late-life infatuation that consumed him. Anna was studying at the Academy of Arts, and Mendeleev, who had developed an interest in art and aesthetics, became a patron and then a suitor. He pursued her relentlessly, and eventually she agreed to marry him. But there was a problem. Mendeleev was still married to his first wife, Fizva. Divorce in Russia required a 7-year separation and permission from the Orthodox Church. Mendeleev couldn't wait. He was obsessed with Anna and convinced she wouldn't wait for him. So in 1881, after obtaining a reluctant divorce that technically wasn't yet complete according to church law, he married Anna. This made him a bigamist in the eyes of the Orthodox Church and Russian society. There was scandal. Some called for his dismissal from the university. The church refused to recognize the marriage. But Mendeleev, stubborn and unconventional as always, didn't care. When confronted about the impropriety, he reportedly replied, "Mendeleev has 2 wives, yes, but I have only one Mendeleev." The marriage to Anna was happy, far happier than his first. They had 4 children together, and Anna provided the emotional support and stability that Mendeleev had lacked in his first marriage. She managed his household, protected his working time, and gave him the domestic peace he needed to continue his research. But the scandal had consequences. Mendeleev's relationship with the university administration deteriorated, and in 1890, after a dispute over student protests, Mendeleev had sympathized with students calling for reforms. He was forced to resign his professorship. He was 56 years old and suddenly without his academic position, but Mendeleev was too prominent to remain unemployed. In 1893, the Russian government appointed him director of the Bureau of Weights and Measures, essentially making him responsible for standardizing measurements across the vast Russian Empire. He took the position seriously, modernizing Russia's system of weights and measures, introducing the metric system, and working to ensure accuracy in commercial transactions. It wasn't pure research, but it was important practical work, and Mendeleev threw himself into it with characteristic energy. He also continued to write, publishing works on economics, industry, and Russian development. He became an advocate for Russia's industrialization, arguing that the country needed to develop its natural resources and build modern industries to compete with Western Europe. Mendeleev was also a man of wide-ranging interests and strong opinions. He studied art and wrote about aesthetics. He investigated Russian oil fields and made recommendations for the petroleum industry. He traveled in a hot air balloon to observe a solar eclipse, nearly dying when the balloon caught fire. He advocated for Arctic exploration and proposed ambitious schemes for developing Siberia. He corresponded with scientists and industrialists across Europe. He could be charming and generous, but also stubborn, temperamental, and occasionally autocratic. His students remembered him as brilliant but demanding, capable of inspiring lectures but also of harsh criticism. He was, in short, a force of nature, brilliant, difficult, endlessly curious, and convinced that Russia could and should become a scientific and industrial power. Dmitri Mendeleev died on February 2, 1907, in St. Petersburg, at age 72 from influenza. His funeral was a major event. Thousands lined the streets, and students carried a large periodic table in the procession, a fitting tribute to his greatest achievement. He was buried at the Volkovo Cemetery in St. Petersburg, and his grave became a place of pilgrimage for chemists and students. Russia mourned the loss of its greatest scientist, the man who had brought international recognition to Russian chemistry and had given the world a fundamental organizing principle for understanding matter. But Mendeleev's greatest legacy wasn't just the periodic table as he published it. It was the concept that elements follow a periodic law, that their properties repeat in regular patterns based on their atomic structure. The periodic table we use today looks somewhat different from Mendeleev's original. We now organize elements by atomic number of protons, rather than atomic weight, which explains why Mendeleev sometimes had to reverse the order. We've added the noble gases, an entire column of elements unknown in Mendeleev's time. We've added the lanthanides and actinides, the inner transition metals. We've added synthetic elements that don't exist in nature, created in laboratories and particle accelerators. The modern periodic table has 118 confirmed elements, nearly double the 63 that Mendeleev worked with, yet the fundamental insight remains Mendeleev's. The periodic table is the central organizing framework of chemistry. Every chemistry classroom in the world has a periodic table on the wall. Every chemistry student memorizes at least parts of it. When you learn that elements in the same column have similar properties, that lithium, sodium, and potassium are all reactive metals, that fluorine, chlorine, and bromine are all reactive nonmetals, you're seeing Mendeleev's periodic law in action. The table predicts chemical behavior, guides the synthesis of new materials, and reveals relationships between elements that aren't otherwise obvious. In 1955, element 101 was discovered and named Mendeleevium in honor of Mendeleev, a rare tribute, as elements are usually named after places or mythological figures, not individual scientists. Mendeleevium is a synthetic element, created in a particle accelerator, existing for only a few hours before decaying. Mendeleev never imagined such elements were possible, yet they fit into his periodic table exactly where they should. The table he created has proven robust enough to accommodate discoveries he couldn't have anticipated: radioactivity, isotopes, quantum mechanics, nuclear physics, all fit within the framework of the periodic law. The deeper explanation of why the periodic table works came only with quantum mechanics in the 20th century. We now know that the periodic patterns arise from the arrangement of electrons in atomic orbitals, from the exclusion principle that prevents electrons from occupying the same quantum state, from the shell structure of atoms. Mendeleev couldn't know this. The electron wouldn't be discovered until 1897, 10 years before his death, but he had intuited the pattern correctly. He had found the organizing principle without understanding the mechanism, had revealed the structure without knowing the cause. This is the mark of a great discovery in science. It captures something true and fundamental even when the discoverer doesn't fully understand why it's true. Mendeleev's journey from the youngest child of a Siberian schoolteacher to international scientific fame is remarkable not just for his achievement, but for what it reveals about the power of pattern recognition, bold prediction, and stubborn conviction. He saw order where others saw chaos. He was willing to leave gaps in his table, to predict elements that didn't yet exist, to reverse the order when chemistry demanded it, to trust the pattern even when the data seemed uncertain. This combination of insight and audacity is rare, and it changed chemistry forever. Today, when we look at the periodic table, printed in textbooks, hanging on laboratory walls, memorized by students worldwide, we're looking at more than a chart of elements. We're looking at the crystallization of Mendeleev's insight, the vindication of his predictions, and the testament to a nearly penniless Siberian boy whose mother sacrificed everything to give him an education. The elements remember. In every column and row, in every periodic pattern, in element 101 named Mendeleevium, Mendeleev's legacy endures. He gave us the map of matter, the guide to the building blocks of the universe, and showed that even in the apparent chaos of chemical properties, there is deep, beautiful, predictable order. That order is the periodic law, and it will remain one of the foundations of science as long as chemistry is practiced and understood.